Come on, my dears, let us proceed further in chapter number 4. Last time we had finished the discussion of one optical phenomenon called interference, correct? Today we will study about another optical phenomenon called diffraction. Diffraction is a phenomenon which is possible for all types of waves. Might be light waves, might be sound waves, might be water waves, correct? Who had discovered this phenomenon? It was Mr. Grimaldi who had discovered this phenomenon called diffraction. Mr. Grimaldi, correct? Fine. Now, first of all, try to understand the limited meaning of diffraction. What do you mean by diffraction in a limited sense? Look, meaning of diffraction in a limited sense is bending of waves at the edges of an obstacle is called diffraction. Bending of waves at the edges of an obstacle is called diffraction in a limited sense. Now let me quote some examples so that you will understand this limited meaning, okay? First, consider these parallel light rays, which are made incident on this wooden pencil. This is a wooden pencil, okay? And just behind this pencil we have kept one screen, okay? Now tell me, wood is opaque to light. So when you make light incident on some wooden substance, that substance is not going to allow light to penetrate. So when light waves cannot penetrate this wooden pencil, you can expect shadow of this object just behind it, okay? So we should get shadow of this pencil on this screen, correct? Yes, we get the shadow, no doubt about it. Here is that shadow. But you just kindly observe the edges of this shadow very minutely. When you observe the edges of the shadow very minutely, then you will notice that these edges are not very sharp. They have some blurred image, faint image. The intensity of light does not become zero at once. It becomes zero gradually, making these edges diffused, okay? Because of what reason do you get such edges? Simple, very simple. When light waves are propagating, if anything comes in the way, it would become an obstacle for light waves. Right now, obstacle is in the form of a wooden pencil. Now, when light waves are made incident at the edges of this obstacle, light waves get bent. From this edge, whichever light waves are bending this way, from this edge, whichever light waves are bending this way, these bent light waves enter in that region where we expect shadow on the screen. Naturally, if light waves would enter in the region of shadow near the edges, naturally the edges will not be very sharp. So this sort of edge which is faint, which is blurred image, intensity of light decreases to zero gradually. Such thick edges we are getting, not very sharp. It is because of bending of light waves at the edges of an obstacle, correct? Bending of waves at the edges of an obstacle is called diffraction, Simple. Let me quote second example. Think of sound waves. In your house, when you just shout from any room, any other family member might be sitting in any another room, he can hear your voice, correct? Why? Because when you had shouted, these sound waves were generated from your throat. those sound waves happen to be incident on various objects in that room, and every object has got some typical dimension, and when those dimensions are over, that is the range of that substance, and it must have some age near the when the material of the substance is getting over, at that surface you must be having that age. So every object has got its own ages, and when sound waves are made incident on those ages, they will be getting bent, and after getting bent, these sound waves are spread all over. That is why the other person can hear your voice from any direction in any corner, correct? This is because of bending of sound waves. It is nothing but again diffraction of sound waves, correct? Bending of waves at the edges of an obstacle is called diffraction. Fine. Now let us give third example. It is regarding water waves, correct? Here we perform one experiment in which we take one big aluminum dish in which we fill up water, and on the water surface when we keep some stick, and using electric motor, when we give that stick some vertical up and down oscillations with a fixed amplitude and fixed frequency, then water waves start propagating on the water surface in the form of linear water waves. Such whole experimental arrangement is known as ripple tank. Ripples means waves, tank means some vessel in which you can fill up the water, and on the surface of water you can have propagation of water waves. Such an experimental setup is known as, ripple tank. So here is the ripple tank in which there is a water surface. On the water surface we keep some stick, and the stick is given up and down oscillations, correct? When you give the stick up and down oscillations with a fixed amplitude and fixed frequency, it so happens that on this water surface, water waves start propagating, linear water waves. The part of the water which is lifted up becomes crest, the part which is depressed down becomes trough. Crest, trough, crest, trough, crest, trough, like that. Linear water waves start propagating on the water surface. And here I have shown only crest I have shown here, correct? Between two consecutive crests, there is a trough, but I have not shown, okay, fine. Distance between two consecutive crests is known as wavelength, shown by symbol lambda. Now just do one thing, when these waves are propagating, you just put some obstacle in the way in the form of two sharpened wedge-shaped wax blocks. Two sharpened wedge-shaped wax blocks. These wax blocks are this, okay? They have sharp corners, pointed corners, and sharp edges also. Now what happens? Between these two pointed ends, we have some open gap, which is normally called slit. So this much distance would give you width of the slit, let it be small d. Now when these linear water waves pass through this slit, it so happens that they get bent. They no longer remain linear, now they have become curved. This is the effect of bending of waves, and that very physical effect is only known as diffraction. Bending of waves at the edges of an obstacle is called diffraction, but in a limited sense. Then you may ask, what is the wide sense of diffraction? Correct? What is the general meaning of diffraction? Look, when you put this obstacle, naturally the whole wave front will not pass through the slit. No, only this limited part can pass through the slit. So whatever physical effect of bending you have noticed on the right hand side of the slit, it is due to limited part of a wavefront. It is due to limited part of a wavefront, and that very physical effect is only known as diffraction in a wide sense. So just tell me the second definition of diffraction. Look here, physical effect arising due to limited part of a wavefront is called diffraction in a wide sense. Physical effect arising due to limited part of a wave front is called diffraction in a wide sense. Got it? Fine. Now here I would like to find out on which factor does amount of diffraction depends. Whether waves will be getting bent by less amount or by more amount. On which factor does it depend? That is what I want to find out. Come on. Do one thing. You just increase this ratio lambda upon d. Correct? How can you increase? Three ways. Keeping denominator constant, you can increase numerator, or keeping numerator constant, you can decrease denominator, or you can do both. You can increase numerator, you can decrease denominator. In short, this ratio will increase. At that time, we find on right hand side that these waves are getting bent by more amount, meaning thereby amount of diffraction has been increased. Correct? Now you just decrease this ratio lambda upon d. How would you decrease? Three ways. Keeping denominator constant, you may decrease numerator, or keeping numerator constant, you may increase denominator, or you may do both. You can decrease numerator and you can increase denominator. Then this ratio will decrease. At that time, on this right hand side, we notice that the waves are getting bent by very slight amount. That is, amount of diffraction has been decreased. Fine. And at last, suppose we keep lambda upon d constant by changing lambda and d both. How? Suppose you are making lambda doubled, you make d value also double. So 2 will cancel, lambda upon d will remain constant. At that time, we notice that there is no change in amount of bending of waves, no change in diffraction, amount of diffraction remains same, constant. So tell me from these observations, when lambda upon d increases, amount of diffraction increases. When lambda upon d decreases, amount of diffraction decreases. When lambda upon d remains same, amount of diffraction also remains same. So it is that ratio lambda upon d on which amount of diffraction depends. Which ratio? Lambda upon d, where lambda is called wavelength of waves and d is called width of the slit. Got it? Please remember this result because we are going to use it in the later discussion. Come on. Amount of diffraction depends on which ratio? Lambda upon d. Please remember. Now let us explain one phenomenon. See, you must have noticed that if you got some room and in that room there is a door, and suppose that door is open, there are two persons standing on either side of that open door, and suppose they are not in the line of sight of each other, so naturally they will not see each other. But however, if one person shouts, then another person can hear. Okay? Why? The reason is that through the open door, which behaves like a very wide slit, it so happens that light waves, when they pass, they do not diffract. Almost amount of diffraction is nearly zero. And that's why the two persons cannot see each other. But when sound waves pass through the open door, they get bent at the edges of that open door by very large amount. So sound is getting spread all over, and that's why two persons can hear the voice of each other. Okay? But let us prove this result. Very negligible diffraction of light waves and very appreciable diffraction of sound waves. Let us prove now theoretically. Look. Here I am writing for visible light. The range of visible light waves regarding wavelength in the electromagnetic spectrum is from 4000 angstrom to 8000 angstrom. Let me take some intermediate value, say 6000 angstrom. Correct? Convert angstrom into meter, multiply by 10 raised to minus 10. Correct? This is 10 raised to 3, this is 10 raised to minus 10. So 10 raised to 3 minus 10, that is minus 7. 6 into 10 raised to minus 7 meter. What is the width of the slit? Right now that wide open door we are taking as slit, and width of the slit means right now width of the door, which you may take nearly 1 meter. Let me find out lambda upon d. Come on, lambda upon d. It will be this upon this. It is 6 into 10 raised to minus 7, which is 0.000006. Now this value of lambda upon d, you can see it is nearly 0. Nearly 0. When lambda upon d is extremely small, naturally amount of diffraction also will be extremely small, because amount of diffraction depends on ratio lambda upon d. When lambda upon d is extremely small, amount of diffraction of light waves will be extremely small. Almost light waves do not diffract at the edges of wide open door, and that's why two persons standing on either side of an open door cannot see each other. Okay, fine, if they are not in the line of sight of each other. Fine. Now let us talk about sound waves. In our day-to-day life, whatever speech we have, it has frequency of sound waves ranging from 100 to 400 hertz. We can take any intermediate value. Suppose conveniently I am choosing this value, frequency 332 hertz. Now don't you know V equals to F lambda? So what is lambda? V upon F. Lambda will be V upon F. What is V? Right now take it as velocity of sound waves in atmosphere at STP. At standardized temperature and pressure, the value of velocity of sound in air is found to be practically 332 meter per second, and frequency conveniently we have chosen to be 332 hertz. This upon this, answer is 1, unit of lambda is meter, and D is the width of the slit, and we are taking the same door as width of the slit, so it will be still 1 meter only. The door remains same. Earlier also width was 1 meter, now also width is 1 meter. Find out lambda upon d. This upon this, 1 upon 1, that is 1. Meter upon meter will cancel. Now compared to this value is very large. When lambda upon d is very large, amount of diffraction of sound waves would be very large, and that's why sound waves are spread all over, and hence the two persons standing on either side of an open door can listen the voice of each other. So this phenomenon is due to negligible diffraction of light waves and appreciable diffraction of sound waves. Got it? Remember once again, amount of diffraction depends on ratio lambda upon d, where lambda is the wavelength of waves used in the experiment and d is the width of the slit. Got it? Fine. Come on. Fraunhofer diffraction of monochromatic light produced by single slit. Monochromatic light is that light which has single wavelength or constant wavelength, or you may take constant frequency. Fine. And what do you mean by Fraunhofer diffraction? I'll tell you. Consider a slit from A to B. This much is the width of the slit. Okay. On this much wide slit, what I do, I make parallel light rays having wavelength lambda incident on the plane of the slit perpendicularly. Fine. When light rays are parallel, tell me, whenever light rays are parallel, the wavefront is plane wavefront. That's why here I am showing plane wavefront. Okay, fine. Now tell me, did we study during the propagation of wave, what happens? The wavefronts seem to be in motion, correct? During the propagation of wave. In the direction of propagation of wave, you can think of motion of wave fronts. So, as these light waves propagate this way, this wave front seems to be in motion, and finally it will be incident here also on this slit. Now tell me, this whole wave front cannot pass through this slit. Only limited part will pass. Only limited part will pass. And you know, physical effect arising due to limited part of a wavefront is called diffraction in a wide sense. So here diffraction will definitely take place. But whenever in a given diffraction, if wavefronts cut by the slit are plane wavefronts, wavefronts cut by the slit are plane wavefronts, then type of diffraction is called Fraunhofer diffraction, which is the name given in the memory of scientist Mr. Fraunhofer. Whenever wave fronts cut by the slit are plane, the type of diffraction is called Fraunhofer diffraction. Okay, fine. Now let us do one thing. Let us place on right hand side some convex lens, and on the focal plane of this convex lens we just place this screen. Fine. Now here it so happens that on this wavefront, according to Huygens principle, each and every point will behave like self-independent secondary source, and it will emit in the forward direction, it will emit secondary spherical waves. So you may consider emission of secondary spherical waves in this direction, in this direction, in this direction, and in this lower directions also. Okay, the way you have shown the rays on the upper side, you may show rays on the lower side also, no problem. Now out of such infinite number of rays, if you consider such rays, look here, they are going straight without getting bent. These secondary light rays are not getting bent, no diffraction for these secondary light rays. That's why no diffraction means we say they are not bent by any angle, so angle of diffraction is 0. So right now you just consider this group of light rays for which angle of diffraction is 0, which are going straight without getting bent. They are made incident on this convex lens, and what is the job of convex lens? Whichever light rays are made incident on it, which are parallel to its principal axis, will be getting focused by this convex lens on its principal focus. So here is the principal focus for this convex lens, where all these light rays will be superposing, correct? Fine, will be getting focus. Fine. Now this theory we will discuss in 3 parts. First part is central maximum, another part is different order minima, and the final part is different order maxima. Let us take all the 3 parts one by one. First of all, let us discuss this central maximum. Come on. For central maximum, you consider these light rays which are not getting bent, going straight. Okay, fine. Now they are focused by this convex lens at its principal focus, which is nothing but central point on the screen. Let it be shown by symbol C. C for central. Okay, fine. Now tell me, if you notice carefully, then you will find that this path length from here to here is the shortest path, and compared to this shortest path from here to here, this path is the longest path, correct? So what you will think, that after coming to this boundary, each and every point on this wavefront will behave like self-independent secondary source, and it will emit secondary light rays, correct? But you will notice that this light ray has to travel minimum distance, and this light ray has to travel maximum distance. So at first thought, what will be the first thought in our mind, that because this light ray has to travel shortest distance, that light wave should reach here earliest, and because this light ray has to travel maximum distance, it should reach here the latest. But no, you know what is observed? All the light waves here are getting superposed at the same moment. Just notice carefully, this light ray has to travel minimum distance in air, but maximum distance in glass, correct? And conversely, this light ray has to travel maximum distance in air, but minimum distance in glass. Ultimately, it so happens that all the light waves superpose at point C simultaneously, correct? Now tell me, all the light waves are coming here at the same moment, as if they have traveled equal distances in the same medium. Then if they travel equal distances in the same medium, then we will say path difference is 0. but here there is a change of medium. Here it is air medium, here it is glass medium. So whenever there is a change in medium, don't say simply path difference, say optical path difference. Say optical path difference. That's why optical path difference I am going to take 0, because all the light waves are coming here at the same moment. If one light wave is coming earlier and the second light wave comes later, then we will say there is some optical path difference. But right now all the light waves are superposing at point C at the same moment, so we can say there is no optical path difference. Fine. So optical path difference between superposing waves at point C is 0. Tell me, what was the condition for constructive interference? Condition was that path difference must be equal to n lambda. Put n equal to 0, then you will get optical path difference 0. So now whenever optical path difference is 0, type of interference must be constructive, and if it is constructive interference, then here you can expect, come on, maximum intensity. So intensity is maximum, that point will appear the brightest because of maximum intensity. So this point is not only central point on the screen, but intensity of light is maximum. So combine these two words, that's why we call this point C as central maximum. Central maximum. So now onwards point C should be regarded as central maximum. Fine. And now think of this light rays. Look, these light rays which are bent by same angle on upper side, same way you can consider on lower side also. At present we consider those light rays which are bent by same angle on upper side, and that same angle I am taking as theta. Fine. So this is the group of light rays which are bent by angle theta, and if this angle theta is less, we say amount of bending is less, diffraction is less. If value of theta is more, we say amount of bending is more. Because theta gives you measure of amount of diffraction, we call this theta as angle of diffraction. What do we call it? Angle of diffraction. So now consider this group of light rays which are bent by angle theta, and now they are focused by this convex lens at some other point on the screen. Let that other point be shown by symbol Z1. Why the symbol is Z? Why it is Z1? I'll tell you, wait. Now tell me, from point A you just draw one perpendicular on this light ray, okay? The foot of perpendicular is point M. Come on, this point I am taking as point Y, this point is X. Tell me, this is the midpoint of this line segment. This is the midpoint of this line segment, correct? You have studied in one of the theorems in 10th standard that the line segment joining midpoints of two sides in a triangle is parallel to third side and half of third side. Half of third side. So measurement of this line segment will be half of this. Sure? So if BM value, suppose I am taking lambda, BM value I am taking lambda, then this XY value will be half of this. Half of this means, come on, lambda by 2. Correct? So distance XY I am going to assume, come on, lambda by 2. Wait. Now once again we make parallel incidence, and for light rays which are parallel, come on, the wavefront will be plane wavefront, correct? Light rays are made incident normally, that is perpendicularly on the plane of the slit. And because light rays are mutually parallel, the wavefront has to be plane wavefront. Fine. As this wavefront moves ahead, look here this way, finally it will be incident on the slit. And now according to Huygens principle, each and every point on any wavefront will behave like self-independent secondary source, and it will emit in the forward direction secondary spherical waves. Now you just consider at present only these two secondary sources, point A and point X, point A and point X. Fine. Now the light waves emitted from point A and point X, they reach at this point Z1. But as compared to light ray emitted from point A, as it reaches point Z1, compared to that light ray, the light ray emitted from X and then reaching Z1 has to travel this much additional distance. So this much additional distance will give you path difference between these two light rays. So what is that path difference? Come on, xy. Path difference is, optical path difference is right now xy, and it is assumed to be lambda by 2. Suppose this angle is theta, then this angle also will be theta. Why? Angle between two given line segments and angle between their perpendiculars are always equal. So if this angle is theta, this also will be theta. Now value of this angle is such that, suppose its opposite side xy is measurement wise, suppose it is lambda by 2. Suppose you have used red light which has wavelength say 6000 angstrom. Then this much value I am just assuming to be 3000 angstrom. 3000 angstrom means what? Half of 6000. So it is 6000 upon 2. 6000 angstrom is lambda. So I am just assuming to be lambda by 2. Now tell me, what was the condition for destructive interference? Condition was that path difference should be equal to 2n minus 1 lambda by 2. Just put n equal to 1. Then you will get path difference lambda by 2. So in case of destructive interference, path difference is lambda by 2. Just pick opposite. If path difference is lambda by 2, type of interference must be destructive. So between the light waves emitted from points A and X, destructive interference will take place at Z1. And because of destructive interference, come on, intensity would be 0. And intensity is 0. But tell me, whenever intensity is 0, point will appear dark point. But wait, do you have only these two as points on this wavefront? On this wavefront, there are only 2 points? No, there are innumerable number of points. Innumerable. You cannot count it. But let us do one thing. Let us divide this whole width of the slit into 2 equal parts, so that each equal part will have same width equal to d by 2. D by 2. Okay. Now tell me. Take this point as suppose A1 and take this as suppose x1. The way between A1 and x1 the path difference is lambda by 2. Just below A1 you take A2. Just below x1 you take x2. So between A2 and x2 also path difference will be lambda by 2. Between A3 and x3 also path difference will be lambda by 2. Dash 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 dash. I mean to say, corresponding to every point in part AX, you can have one point in corresponding part XB such that the light waves emitted from which, when they will reach at point Z1, will have path difference lambda by 2. And if path difference is lambda by 2, type of interference will be destructive, intensity would be 0. In short, this half of the slit nullifies the effect of this half of the slit, and because it cancels the effect, the ultimate resultant intensity of light at this point Z1 would be 0. Intensity is 0. Intensity is 0. The word is 0. What is the first letter of that word? Z. That's why I am giving the symbol Z. So you will remember very easily. Z point means 0 intensity. Z point means 0 intensity. And because this is the very first time intensity becoming 0, we call it first order minimum. First order minimum, first order. That's why the symbol is Z1. Got it? The way you got first order minimum on the upper side, same way at the same distance from the center maximum, you will get first order minimum on the lower side also. So these two first order minima are equidistant from the central maximum. Got it? Now, what is the condition for any point on the screen to become first order minimum? What is the condition? I am showing you. Now, if this is theta, this also will be theta. Why? Angle between two given line segments and angle between their perpendiculars are always equal. Remembered? Perpendicular to this is this. Perpendicular to this is this. So, if this is theta, this also will be theta. Just find out sin theta. Come on, I want sin theta. In this right angle triangle, find out sin theta. Opposite to theta, which is xy, correct? Divided by hypotenuse, which is opposite to right angle, which is ax, and divided by hypotenuse. Opposite upon hypotenuse. What is opposite to theta? Come on, xy, divided by hypotenuse opposite to right angle, which is ax. Here it is ax. opposite upon hypotenuse. What is xy? What is xy? Lambda by 2, lambda by 2. What is ax? What is ax? Come on everybody, d by 2, d by 2. 2 will cancel, giving you lambda upon d, giving you lambda upon d, correct? But instead of theta, I just write theta 1 because at present I am talking about first order minimum. That's why angle of diffraction should be shown by this symbol theta 1. Then you will realize it is angle of diffraction for first order minimum. That's why. Come on. Similarly, if you obtain condition for second order minimum, the condition is this: sin theta 2 equals to 2 lambda upon d. For third order minimum, sin theta 3 will be equal to 3 lambda upon d. Why don't you tell me in general? Whatever is the suffix here, same is the multiplier here. If suffix here it is m, here also you can write m. So sin theta m equals to m lambda upon d. Sin theta m equals to m lambda upon d. Correct? This gives you condition for any point on the screen to become mth order minimum. What is m? Order of minimum, and that you can change like 1, 2, 3 dash dash dash. Correct? Fine. Now we go for the last part of this theory, different order maxima. Why this word is maxima? I'll tell you. Now tell me, what is the difference between this figure and this figure? There are 2 points of difference. One is, instead of having 2 equal parts of the width of the slit, here I have divided width of the slit into 3 equal parts. That's why each equal part has width. Come on, d by 3, d by 3, d by 3. Correct? And one more thing, I have considered greater angle of diffraction, greater than theta. Let it be theta dash. Okay? Now consider this group of light rays which are bent on upper side with the same angle of diffraction, say theta dash. And because they are bent by same angle of diffraction, they have to be mutually parallel. Let them be focused by this lens at point M1 on this screen. Fine. Why the symbol is M1? I'll tell you, wait. If this angle is theta dash, I say this angle also will be theta dash. Same fact. Angle between two given line segments and angle between their perpendiculars are always equal. Come on. Now draw one perpendicular from point A on this light ray. Let the foot of perpendicular be M. And this point is x1, this point is y1, this point is x2, this point is y2. And now, if this much is lambda by 2, this much will be double than this, double than lambda by 2. So, x2, y2 will be lambda, x2, y2 will be lambda. And this bm will be 3 times than this. This much is lambda by 2, 3 times than that, so it is 3 lambda by 2. Got it? Fine. Now tell me, as compared to light wave emitted from point A, the light wave emitted from point x1 has to travel this much additional distance in order to reach at point m1. So this much additional distance will give you path difference. Path difference. So path difference is x1 y1. Come on, path difference is x1 y1. Suppose the value of angle shown in the diagram is such that its opposite side, that is x1 y1, by measurement, suppose it is lambda by 2. If x1 y1, which is optical path difference, if it is lambda by 2, when optical path difference is lambda by 2, optical path difference is lambda by 2, which interference will take place? Come on, destructive interference will take place. And because of destructive interference, what will happen? Intensity of light would be 0. But wait, you have considered only 2 point sources. Tell me, on this entire wavefront, there are only 2 points? No, there are innumerable number of points. So now, just give them symbol this way. Take this as A1, take this as x1. A1, x1, what is the path difference? Lambda by 2. Just below A1, you take A2. Just below x1, you should take x2. A2, x2, A3, x3, dash, 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 dash. In short, for corresponding to every point in part A, x1, there is a corresponding point in part x1, x2. the light waves emitted from which have path difference of lambda by 2 while reaching point M1. And because of path difference lambda by 2, destructive interference will take place, and hence the intensity of light due to these two parts at this point would be 0, because this part cancels the effect of this part. No problem. Still the third part is left out, whose effect is not getting cancelled. So at least you will have some intensity of light at this point due to third part of width of the slit, correct? And naturally, because it is the intensity of light due to third part of the total width, naturally here intensity of light would be smaller than what you got in case of central maximum. That's why I am putting here bigger brighter dot. Here intensity is maximum, here intensity is less than that, then I am putting smaller brighter dots, so that you will realize that here intensity is more than 0 but less than maximum, more than 0 less than maximum. We call this point as first order maximum, first order maximum, first order maximum. The word is maximum, first letter is M, that's why I am putting M. And after you got here 0 intensity, when you move up, this is the very first time you are getting maximum intensity, that's why I am putting symbol M1. The meaning is first order maximum, first order maximum. The way you got first order maximum on upper side, you can get first order maximum on lower side also. Both the first order maxima are equidistant from the central maximum. Okay. Now let us obtain condition for maximum. Okay. Come on. Now when this angle is theta dash, this also will be theta dash. And now just find out sine of theta dash. Sine of theta dash means what? Opposite to theta dash divided by hypotenuse. Opposite to theta dash, come on, x1 y1, here it is x1 y1, divided by hypotenuse, which is opposite to right angle, which is ax1, ax1. What is x1 y1? Come on, x1 y1 is lambda by 2. Put it here, lambda by 2. What is ax1? Ax1 is d by 3, d by 3. 3 will go up, 2 will come down, 3 lambda upon 2d, 3 lambda upon 2d. Right now you are talking about first order maximum. That's why this is the angle of diffraction for first order maximum. Let it be shown by symbol theta 1 dash, theta 1 dash. Fine. Can you rewrite 3 by 2 as 1 plus 1 by 2 into lambda upon d is always there? No problem. Now the way you got condition for first order maximum this way, if you try to attempt the condition for second order maximum, you will get it this way. Sin theta 2 dash, it is 5 lambda upon 2d. So instead of 3 by 2, you are going to get, come on, 5 by 2. And this 5 by 2 can be written as 2 plus 1 by 2 into lambda upon d, correct? So tell me, whatever is the suffix here, same is the number here. Here 1, here 1, here 2, here 2. Come on, here m, here you can write m. So sin theta m dash will be equal to m plus 1 by 2 into lambda upon d. M plus 1 by 2 into lambda upon d. Tell me, what does this give you? Condition for mth order maximum. Condition for mth order maximum. This was condition for mth order minimum. This is condition for mth order maximum. What is the difference? Here angle of diffraction is theta m. Here angle of diffraction is theta m dash. Here only m. Here m plus 1 by 2. Here m indicates order of minimum. Here m indicates order of maximum. Here m values are changing 1, 2, 3 dash dash dash. Here also m values are changing 1, 2, 3 dash dash dash. Got it? Fine. Now let us distribute intensity of light, correct, on this screen. And for having the distribution of light, distribution of intensity of light on the screen, we have one formula, the derivation of which is not in your syllabus. You are supposed to remember that formula directly. Very simple formula. I theta equals to I0 sin square alpha upon alpha square. I theta equals to I0 sin square alpha upon alpha square. Let me give identification of each symbol. What is I theta? Intensity of light corresponding to angle of diffraction, say theta. I0 is maximum intensity of light. Alpha is some sort of angle. It is related to angle of diffraction theta by this formula. Alpha equals to pi d sin theta upon lambda, Wait. Let me derive one simple formula. They have not derived in the textbook. It will be helpful to you in the numericals. Wait. Let me apply this formula for mth order maximum. Then instead of theta, you may write here theta m dash. Theta m dash. Wait. This pi d upon lambda as it is. Pi d upon lambda as it is. Instead of theta, when you write theta m dash, you will get it here sin theta m dash. Sin theta m dash. Sin theta m dash is how much? M plus 1 by 2 into lambda upon d. Here it is. M plus 1 by 2 into lambda upon d. Now they look here. dd will cancel. Lambda lambda will also cancel. M plus 1 by 2 as it is. Pi also as it is. Fine. Now what is m here? Order of maximum. And that you can change like 1, 2, 3 dash dash dash. You may put m equal to 1, 2, 3 dash 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 here. Every time you can find out different values of alpha. When you substitute those values here, come on, sin alpha is either plus 1 or minus 1. But sin square alpha is always 1. Sin square alpha is always 1. So here sin square alpha is 1. Come on. When sin square alpha is 1, just put it here. Sin square alpha is 1, put it here. So you get I0 upon alpha square. Come on, I0 upon alpha square. I0 upon alpha square. But alpha square means what? Square of this. Come on, m plus 1 by 2 whole square into pi square. But mind well, this formula you should apply for finding intensity of light for mth order maximum. Mth order maximum. Suppose you take m value equal to 1. If you take m equal to 1 and then put pi value 3.14, simplify, you will get intensity of light at first order maximum as I0 upon 22, nearly, approximately. Then for second order maximum, intensity is I0 upon 62. For third order maximum, intensity light is I0 upon 121, like that. So what have you noticed here? As order of maximum increases, first to second, second to third and so on, then denominator goes on increasing, so the ratio will go on decreasing. In short, this intensity will go on decreasing. Here also you can see, when m will increase, because it appears in the denominator, when m will increase, come on, this intensity will go on decreasing. As order of maximum increases, intensity light goes on decreasing. Using this formula, if you plot a graph of I versus theta, the graph is this. I versus theta, the graph is this. Look, correct? This is the graph which gives you intensity of distribution of intensity of light on the screen. This is the point which is central point. That's why I'm putting C, where intensity of light is maximum, correct, equal to I0. We call it central maximum. Where the intensity of light becomes 0 very first time, we call it first order minimum, Z1. Becoming second time 0, Z2. Becoming 0 third time, Z3. Becoming 0 first time, Z1. Second time, Z2. Third time, Z3, correct? In this part, here intensity of light is maximum and we call it first order maximum, symbol is M1. No doubt this intensity is in this much part it is maxima, but however it is smaller than this, it is nearly 22th part. It is 1 upon 22 times I0, 1 upon 22 times I0. And here intensity of light is still smaller than this, it is I0 upon 62, fine. As order of maximum increases, intensity goes on decreasing, correct? What is this? Tell me. First order minimum. This is also first order minimum. If you find out this much linear distance between two first order minima on either side of central maximum, then that linear distance is called linear width of central maximum. Linear width of central maximum. If we say only width of central maximum, we mean to say linear width. And how much is that linear width? Let us find out its formula. Look, here is first order minimum, correct? On upper side. This is first order minimum on lower side. Suppose this much distance is x1. This is also x1. So from here to here, it will give you distance between two first order minima on either side of central maximum. And this distance, which is 2x1, will give you linear width of central maximum. So let us find out formula of 2x1, which is linear width of central maximum. Come on. Because this is first order minimum, let me find out sin theta 1. Sin theta 1. This is minimum. Apply condition of minimum, this one. Correct? and put m equal to 1. Put m equal to 1, then sin theta 1 will be equal to lambda upon d. When you put m equal to 1, it will giving you lambda upon d. So sin theta 1 is lambda upon d. And if angle of diffraction is very small, then sin theta 1 is nearly equal to theta 1. Okay. So theta 1 is lambda upon d. Wait. Now in this triangle, correct? This is the angle of diffraction corresponding to first order minimum. First order minimum. That's why I am putting symbol theta 1. Just find out sin theta 1. Come on, because theta 1 is very small, sin theta 1 can be taken nearly equal to tan theta 1. Sin theta 1 is nearly equal to tan theta 1 provided theta 1 is very small. And tan theta 1, just find out in this triangle. Find out tan theta 1, it is opposite to theta 1, which is x1 upon adjacent side. Adjacent side will give you xc, this much distance, correct? But this much distance is distance between slit and screen. Let it be shown by symbol capital D. So in short, sin theta 1 is how much? x1 upon d. But what is sin theta 1? From here. From here sin theta 1 is, come on, lambda upon d. Sin theta 1 is lambda upon d. Come on, this sin theta 1 is lambda upon d, correct? And this x1 upon d as it is. And now just find out 2x1 from here. Come on, find out x1 first. Take this d here. Come on. x1 will be lambda d upon d. Lambda d upon d. Just multiply by 2 on both the sides. So you get 2x1 will be equal to 2 lambda d upon d. This 2x1 gives you distance between two first order minima on either side of central maximum. The same linear distance is called linear width of central maximum, which depends on capital D. Meaning thereby, if you just take the screen away from the slit, then D will increase and linear width of central maximum will increase. Mind well, this is called linear width. It has got unit meter or centimeter, like that. But let us find out now angular width. The way you have joined this with this, you can join this with this, correct? The way you got this theta 1 on upper side, same way you can get it on the lower side also. So if you take theta 1 plus theta 1, you will get angle between these two light rays, correct? And that angle is called, come on, angular width of central maximum. Angular width of central maximum. I repeat, the way you have shown theta 1 on the upper side, you can just show theta 1 on the lower side also. Then angle between this light ray and this light ray would be 2 theta 1, and that 2 theta 1 is called angular width of central maximum. Let us find out that 2 theta 1 from here. Just multiply by 2. So you will get 2 theta 1 will be 2 lambda upon d. This is called angular width of central maximum, in the formula of which capital D does not appear. Capital D does not appear. So this angular width of central maximum is independent of distance between slit and screen. But in the formula of linear width of central maximum, capital D appears. So linear width of central maximum depends on distance between slit and screen, but angular width of central maximum does not depend on distance between slit and screen. This is formula for linear width of central maximum. This is formula for angular width of central maximum. Got it?